I know not every one of you got through with the handout. That's fine. We will figure it out as we go. Yeah, we just need to synchronize everyone, and if you're jet lagged tomorrow or have some time tonight, you can sort of catch up on these parts. It's not really essential that you have worked through every line of that. I would just like to get you started with the real content of this course, and we need to talk about proteins, so we do some proteomics this afternoon. What I'm going to do now is I'll give you a very rough, very short outline of how we can actually sequence proteins or identify proteins. And there are two fundamental things that we need to discuss here. That is, first of all, the idea of a database search. How can we actually identify proteins? We need to understand how peptides fragment for that, and then how we can search that in a database. And I will show you parts, bits and pieces of these search engines very quickly. Then you can ask questions, and we will start in a hands-on session to actually do that on real-life data. And if something is unclear, you can come to me or to one of the other guys and ask that. So let's talk about peptide database search, and that is when you've done genomics, that is sort of the equivalent of read mapping. We are trying to figure out which peptide comes from which protein. So the first question is, why can we identify peptides based on their mass spectra? That's a non-obvious thing to do. The answer is, so far we have only discussed mass spectrometry, but there's also something that's called tandem mass spectrometry, where we take such a charged ion and we let it collide with neutral gas, and then it breaks apart. And I've shown you the composition of such a peptide. What happens is that if you have such a peptide, you can break it apart basically before and after each and every amino acid. So if such a peptide collides with a neutral gas atom, it'll break apart, and it's not breaking apart at arbitrary positions, but preferentially at the peptide bond. Now, if that happens, remember, this is a charged peptide, a charged particle. If that happens and a bond breaks, then one part of the molecule will retain the charge, and the other part will be uncharged and will not be visible to the mass spec from there on. But the charge can go to both ends, and if the charge goes to the left-hand side of the peptide, so if it breaks here, and the charge part is then YEVE, if the charge is here, then we will actually see this guy in the mass spectrum. If the charge is retained on the right-hand side, we will see GMR. We see a peak for that part. Now, since we do not shoot like 10 peptides in the mass spec, but a couple billion, we will actually see both happening. And how can you determine how likely it is that it breaks at one position? Well, it's the relative intensity of these peaks, because one peak is caused by the left-hand side, another by the right-hand side. So we will see mass spectra like this. And if it breaks here and it then breaks there, we should see two peaks. And what is the difference between the two peaks in mass? Well, it's just the mass of one amino acid. So fundamentally, you could walk these peaks if you know that this guy here is caused by is a Y ion and this guy is a Y ion. You could walk the sequence by looking at the distances between these peaks. The trouble is, if someone shows you the spectrum, you don't know which of these ions are Y ion, which of these ions are B ions. The second issue is that oftentimes that is what spectra look like. So these ion series are incomplete. And if they are incomplete because the cleavage at one position is just chemically less likely than at other positions, then it becomes harder to find these series. So people started looking at database search, basically taking all the possible sequences that we have in the human proteome. That's why we need the genome, post-genomics methods. and compare that to the experimental spectra that we see. So let's look a bit closer at this product ion generation. How does that occur? That's where these famous B and Y ions come from. That's a nomenclature that was proposed by Röpsdorf and Vollmann in 1984. And when you look at the peptide bond, these are two amino acids with their side chains Rm and Rm plus 1, and the carbonyl and the amide moiety of the backbone. If it breaks between at the peptide bond, if this bond breaks, then the right-hand side is what we call a Y ion, and the left-hand side is B ion. What can also happen, depending on the conditions in the mass spectrometer, depending on the peptide, is that you get fragmentation to the left of the carbonyl or to the right of the amide. And then we call them A and X, or C and Z ions. That's all there is to it. Both can be charged, and they give letters. You don't know a priori what's really going to show up in your spectra. You can control that by the conditions in the mass spectrometer to some degree. If we take such a peptide, for example, sequence test peptide, then we can predict where these ions are. How can we do that? Well, we know the masses of the amino acids. You know what monoisotopic masses are by now. We can just say, if I start from the left and from the right, I just can predict what are the masses of the suffix ions and the prefix ions. So to computer scientists, we take the sequence, we take all the suffixes, we take all the prefixes, and we compute the masses of those. Putting them all together should give us a theoretical spectrum that contains all the hypothetical B and Y ions that can be there. But not all of them will be there. And they will have different intensities. If you take only the Y ions, then these letters are comparatively straightforward. The distances here are, well, the masses of the amino acids. And then you can add all the other ions. B ions, they can have doubly charged Y ions, doubly charged B ions. And then you can see this becomes comparatively cluttered pretty quickly. And to make things worse, that's not the only thing that can happen. If this peptide fragments, you can also see so-called neutral losses. That means the ion remains charged, but a neutral molecule sort of falls off. The charge remains, and common losses are water, so you lose 18 Dalton, H2O, or ammonia, 17 Dalton. That can happen on those amino acids that actually have nitrogen in them. Or phosphoric acid. And if that happens on phosphorylated amino acids, of course, if that happens, then you see this loss peak here, a neutral loss peak that appears in the spectrum as well. Yes, please.
Why do you have amino acids only on those amino acids?
Say again?
Why do you have amino acids only on those amino acids, not on all of them?
Not every amino acid can lose ammonia easily. It's about the structure. What's special about these amino acids? Yeah, not all of them are charged. 2 of them are charged. They have an amino group or ammonium group in the side chain. Yeah, they are, and that is what's falling off. It's not falling off at the backbone. Yeah. So this can result in additional peaks. So one component of such a database engine is a theoretical spectrum generator that has simple rules like the ones we discussed, B ions, Y ions, and then neutral losses, and takes a sequence and constructs a theoretical spectrum from that. And the second component that we need is a scoring function, and then we have everything we need for a database search engine. And Mascot, Sequest, OMSA, they all work more or less in the same way. They take an experimental spectrum. They turn that usually into a list of masses. The intensities are often not used for the scoring because they can be very variable. There is more information in the mass of these fragments than there is in the intensity. And then we take a sequence database. For example, all the annotated protein sequences or all the 6-frame translations from a not so perfectly annotated genome. It depends on what you're really looking at. And what do we do with the sequence database? Well, we try to digest it in silico. So we apply trypsin to all of these peptides. Trypsin cuts after lysine and arginine, but not before proline. That's one of the standard rules. And you can construct all tryptic peptides that can arise from one of these proteins. Then you predict these theoretical spectra, and again, you turn them into lists of masses. One second, with you in a second. And then all we do is we compare all these theoretical spectra to these theoretical spectra to the one experimental spectrum that we see, score them, and hopefully the one with the highest score, the theoretical spectrum with the highest score, is the one closest to the experimental spectrum, and thus we would assign the sequence to this particular spectrum. Yes, please.
Yeah. How does a common database search in terms of the intensities of these ions? How do they score? Like how do they take that? Because
Not at all.
Not at all.
Yeah. That's not true for all the search engines, but the majority of search engines uses intensity only to remove some of the peaks, to do some filtering, basically say these are too low intensity, we discard them. But when you compare spectra of the same peptide, you will notice that depending on the conditions, the intensities can vary quite a lot. And that is why people found intensities to be not that reliable. People have also tried to predict these intensities, and that is a very tricky business as well. So prediction of intensities can improve the scoring, but in most of the cases when people tried it, it did not work that well. Okay, so that's the overall schema there. So how can we do that? Now, the database search first of all needs to extract all the sequence candidates, tryptic peptides, and then it looks at the precursor masses of the individual spectrum. Because not all of these peptides are candidates. If we know that the peptide comes from, the Tandem spectrum comes from a peptide that has a mass of 500 Dalton, we need to look at tryptic peptides that are twice as long, that have twice the mass. So we can filter that down usually to a couple dozen, perhaps 100 candidates. That depends on the size of your database, but also on the mass tolerance that you need for the search. Then you generate all the theoretical spectra. Then you align the theoretical spectra. That depends a bit on the scoring function. So you identify which peak in the theoretical spectrum corresponds to which peak in the theoretical spectrum. You score that, and then you report all so-called peptide spectrum matches, PSMs, which is this list. So let's look at the candidate generation. So what we're given is an experimental spectrum, say S, and the task is now to identify the correct sequence for S, given the protein database. So we can define a search space for this sequence S, given a mass tolerance D. Let's assume we know our mass spectrometer is accurate to, say, 20 ppm. Then we know that all the peptide sequences that are further than 20 ppm away in their exact mass from the accurate mass of the precursor peak, we can discard those candidates because they are outside, they are too far away from what we have measured. So basically, this gives us a set, let's call it omega of S, that are the candidates for which this condition holds, so that the measured mass, the accurate mass of the precursor minus the candidate's mass is under this threshold D. Second step is then we try to model a theoretical spectrum. So we generate that just based on the sequence that is in this search space. We can enumerate that by going over the sequence database. There are a couple decent ways to do that quickly. And that gives rise to a bunch of theoretical spectra in this search space, and we just need to compare them to this experimental spectrum. So how is that done? There are a bunch of tools for comparison. The main difference in these search engines is actually how this scoring scheme is implemented, and that means there are also differences with respect to runtime and performance. But fundamentally, they're all based on the same comparison of fragment ions. And comparison can be done in different ways that we will also talk about later today, this afternoon. In reality, such a database search engine can be a bit more complex. This here is a more complex workflow. You also need to have additional experimental data. You need to have information on possible modifications, carbamidylation, you know what I mean, iodoacetamide. The instrument parameters need all be set properly for the search engine. Otherwise, you start seeing funny things popping up. Variable modifications, oxidation, for example. If that is not configured properly and all your methionines are oxidized, you will simply not find anything. If you set the wrong search enzyme, so if you did not digest with trypsin and have the wrong enzyme, then you will not find any candidates. So there are a couple of things. There are also things like contaminants that you want to remove. And then you often also pre-process the database, because this in silico digest you don't have to do every time. You just do it when the database changes. So in detail, this can be arbitrarily complicated. Now let's look a bit into some of these search engines, and I'll only give you glimpses into that, because we're otherwise already we're taking away too much time from the hands-on session. There are a lot of database tools that are currently being used, and they come into fashion and move out of fashion at a certain rate. Some have been with us for a long time. With some, we don't even know what they're doing, particularly with the commercial search engines. There's perhaps a paper out there, but the only thing that you can guarantee is that this paper no longer describes what the search engine does. So you would hope that if you throw the same data at different search engines that you get the same results. Unfortunately, that is not the case, and that is not surprising, because they use different algorithms, they have different parameters, and then you end up with different orderings in these score lists. So one search engine that is popular, also because it's an open source search engine and is also really fast, is Tandem. And there is a good description of Tandem, at least the way it used to be in this paper that I've put here on the slide. What Tandem does is it tries to find overlapping masses. So it's trying to find a peak that is in the experimental spectrum and that also occurs in the theoretical spectrum. And that's one of the oldest scoring mechanisms. It goes back to the 1990s, when people asked, how do you compare mass spectra? Now, when I learned how to interpret mass spectra, that was back in the old days, you know, the other millennium, we did that by books. So we got a mass spectrum, and the way you did it, you took the 3 most intense peak, and then you went to the library. And there were books with indices, and you could just say, I saw a peak at 74, at 53, and 120. And then that would link you to the books in the shelf where the spectra were printed. What was the idea? The idea is really that you can look at the intense peaks, and if they're shared possibly across multiple spectra, then you just need to browse only these spectra. And in the same way, we can use what's called a shared peak count to score these spectra. Because if they are the same, they should share a larger number of peaks than otherwise. Why would they share peaks otherwise if they're different things? Yeah, that's already too complicated. By accident. Yeah? Because if you spread 200 peaks over 300 Dalton, then the odds of just hitting one of these peaks within the mass tolerance is not so small. Yeah, so you will have random matches, but these random matches will have a certain probability. And of course, if you have peptides peaks at the right position, and if it's the same thing, then you should maximize these odds of sharing peaks. And that is at the heart of many of these algorithms. You align these peaks. And you can reduce the spectrum, the experimental spectrum, to only those peaks that are shared with one of the theoretical spectra. And then you can score that, because if you reduce the experimental spectrum to only the peaks that match the theoretical spectra, you can simply use something like a dot product where you look at the intensities. Now we're actually looking at the intensities, but we're not looking at the intensities of the theoretical spectrum, because the theoretical spectrum does not have any intensities. We don't know what the relative intensities are. So what's the rationale of actually using the intensities here? Well, the idea with this dot product with the intensity-weighted shared peaks is that the more of the signal you can explain away with the theoretical spectrum, the better it is. So the idea is basically how many of these ions that my detector saw, how much of the ion current could I explain with this theoretical spectrum. And the larger this score, the better it is. And you would look at all the theoretical spectra and try to score them. Now, one of the things that can happen that is often overlooked is this type of approach also gives you scores if the peptide that you're looking at is not in a database at all. How can that happen? Say again? Missed cleavages, yeah, that's one source. We also discussed post-translational modifications. If there are post-translational modifications to this peptide and you did not tell the search engine to look for this particular post-translation modification, it will miss it. Or if you have genomic variants that translate to different peptide sequence, then this sequence cannot be in your reference proteome. So there are many reasons why this may fail. And that's something we will discuss later this afternoon, how we deal with this type of error. Because fundamentally, the search engine is going to give you a score for every spectrum. Even if it's not a peptide at all, even if it's a metabolite, it will give you a score. Yes? Yeah. Yeah. You sum over all the peaks that are left. Now, we will talk about the statistics of that later on. I will just give you some idea. What we can do is we can look at frequency histograms and ask the question, how likely is it that we see a certain score? I was working a lot with people in proteomics who said, well, if the mascot score is 40 or better, then we believe the peptide. But these scores are not that well behaved. This is not a thorough statistical test. Instead, we can look at what is the expected value of what we see, and we can look at the distribution of these scores. Now, what X-Tandem does is it asks the question, if I see a certain score, what is the probability to have a value greater than that created by random matches? And as I said, random matches can occur as well, have to occur, because you have enough peaks that are distributed over this spectrum. And you can just look at the probabilities of that, and you would then just decide, well, if I know the probability of this occurring by chance, then I can make an informed decision how much I trust that. And that is already hinting at this idea that we will discuss this afternoon, what's the so-called false discovery rate, to what degree can you trust your results. And you would hope that if you have scores that give you a decent score, if you have scores that give you a very high value, you can trust that more than lower scores, which is not always true. Can you imagine why lower scores might occur and why that might be confused with another peptide. What are the effects that can happen there? So, yeah. Low abundance, exactly. That's the main reason for crappy spectra. Because if you have only a very small number of ions that goes into the mass spec, then you will not see all possibilities of this fragmentation. So you end up with peaks or spectra that have low intensity peaks and a small number of peaks, and then of course the identification becomes harder, fundamentally because there's incomplete information in the experimental data. If you go to higher abundances, then you get cleaner ladders for most of these peptides, and that makes it easier to find them. Tandem uses a so-called Hyperscore that's calculated by multiplying the score with the factorials of the number of assigned B and Y ions. And that's based on a hypergeometric distribution, and that rescales these scores in a way that it becomes easier to actually pick up the valid PSMs. And the problem in a way is that you have a mix of hits there. When you look at this Hyperscore that Tandem uses, and you see the number of matches that they have, then you will always get matches that are incorrect, and they tend to have a low score. And you would hope that your best hit here has the highest Hyperscore, and you would hope that your second best hit is sort of lower, and ideally they are separated by quite a bit. In reality, that does not always happen. And what are reasons for that? Well, one of the reasons is that even the incorrect hits can have sufficient similarity in the spectrum. Imagine you have the same sequence occurring in a database, but two amino acids are flipped. So one spectrum reads AL, the other reads LA. Then you still share most of the B ions up to this point and most of the Y ions. So there is also, a degree of incorrectness when it comes to peptide identifications. Even incorrect peptide identifications can be partially right, and that means they will have higher scores than you would expect from totally incorrect scores. But we can use this score distribution to give us some confidence in that. What we can estimate is the E value, and Tandem does that by basically extrapolating based on this distribution what is the expected number of random matches, and you can compute that very easily without going into the details. You can say a score of this value of 60 has a 10% chance of occurring at random, and that gives you some idea of how reliable this particular score is. The different search engines over the years have explored hundreds of scores. I know that we have looked at hundreds over the years, and it's very hard to find good scores. You can look at many different things. You can look at cross correlation. You can look at shifts. Sequest does this with this X-core score by just shifting the spectra and looking how much they still agree. And that gives you sort of a background value. You can use different scores in different search engines, so you can switch different scores on and off, and again you will end up with different results. You should also know what you're looking for. Most of these search engines have been trained for triptych peptides. If you're working with non-triptych peptides, you might again get different scores, something to be kept in mind as well. So before we try that out, I just mentioned a few search engines. Of course, most of you will have heard of Mascot. I've mentioned it already. That's a commercial package that used to be the gold standard for a long time. Phoenix is around, that works reasonably well. Inspect, Mirimatch, Sequest, the commercial one. Comet works really well. OMSA works from time to time. So I'm not going to tell you which search engine is the best one, because I can't tell that. It's going to depend on the data set. It's going to depend on your particular problem. What I can only tell you is that if you stick with the one that has been pre-installed and don't try others, you're giving away an opportunity. Because these search engines, they work on different instruments better than others. They work on different data sets better than others. And I haven't seen a data set where, or I haven't seen a search engine where I could consistently say this search engine is the best one for all the data sets, for all the instruments. It doesn't work that way. Yes, in more than one database, or with more than one search engine? Because the database tends to be fixed for the most part. Yeah, you know, if you're working on yeast, you use a yeast database. I know that people are looking into people that are looking for isoforms of proteins use different databases, and there are different ways to construct them. People also compare search engines, but you will find a certain correlation with co-authors of one of the search engine and success of that particular search engine in the paper, which is not shocking.
So I have the impression that all these algorithms rely on the unit masses. So when you look at the data, it's like 2008, 2007. So I'm wondering what's out there now in terms of the accurate masses, high resolution data.
All these search engines also work on high resolution data, but to varying degrees, and that is one of the reasons why Comet is also working well. But you should be aware of what resolution your spectra have. And the resolution of the tandem spectra is not necessarily the resolution of your mass MS1 spectra. It depends on how it's generated. But we see that some search engines work better on HCD data than on CID data, that's for sure. Petya. I like it. Yeah. It depends. It really depends. I think we can discuss that offline. I like MSGF+, we use it a lot, but we've also run into trouble with it. But my recommendation is just give 2 or 3 search engines a shot, and we will actually show you how you can do that without too much pain, because in OpenMS you can just plug them in and out. You need to be aware of these search settings. That's the OpenMS uses so-called adapters that you call the search engines. You can plug these adapters in the workflow, and here you need to specify the parameters that you know from the instrument, like the precursor mass tolerance, fragment mass tolerance, what unit that is, and then also modifications, carbamidomethylation, now I can pronounce it, and also oxidation, and you can have them either fixed or variable, and depending on that you get different search spaces back. So you have to work with that a little bit and experiment. These mass tolerance settings are easy to know when you know the instrument and when you know that the calibration of the instrument was well done, if you've done it yourself, or trust the person who did it. Depends on who's better. It determines the search space. You can imagine if you open up this window, then the number of candidates just explodes that you pull out of the database. And that can go both ways. If you set it too tight, you might miss the right identification because all your masses are miscalibrated. If you open it too wide, then you will get lots of crap because you're pulling in masses that match only randomly, accidentally, but shouldn't be considered because their masses, precursor masses, are too far off. Another thing to keep in mind is the charge state. You should only consider masses larger than 1 for various reasons. Have you any idea why that? Why greater than 1? Is it 1 charge enough?
Because the ion source and the sign of the charge both contribute to the charge state.
Yeah. if you have triptych peptides, you basically get one charge for free. So they should already have two charges, potentially more if they have additional amino acids that can bear a charge on the side chain. With different fragmentation, different ionization techniques, however, you also see different types of ions. So you need to know that. And if you change the conditions, that might result in different distribution of these charge states. Missed cleavages, that is something that happens. Sometimes these proteases do not cleave perfectly. Sometimes that's also desired. If you know that, you need to put it in, because it basically means that your amino acid, your peptide can also contain lysine and arginines with triptych cleavages. If you know that occurs a bit, you can find new candidates setting this parameter, or you can fix your experiment and make sure your digest is properly done. Whatever is easier. Modifications can happen in various ways. This fixed alkylation, carbamidamethylation, is usually done to alkylate the cysteine. So if you search with the original mass of cysteine, you just wouldn't find that guy. Important to set. But then there are also variable modifications. Methionine can be oxidized to sulfone via sulfoxide. That can happen in some of your peptides or with all of them, depending on what you did to the sample in the pre-analytics. Something to check. Otherwise, you miss all the all the methionines in there. Now, you could argue if that can happen, you just put all of them in as variable modifications. And then you can't miss anything. What's the problem there?
Then your search space becomes extremely large. That can require quite a lot.
How many modifications are there? And how many ways can you modify a peptide? So there's a database that's called Unimod, and the last time I checked, I think that must have grown quite a bit since then. It was over 1,800 different modifications. Now, if you put them all in, then your search space goes up. And do you get more hits? No, you actually get fewer hits. Because at the same false discovery rate, you get fewer hits that are valid. So if you explode the search space, you get random hits everywhere, but you don't get the stuff that is in there. So design your search, design your database also in a way that you search for the stuff that is in your sample. It doesn't help you to search against all possible proteins if you know there's only E. coli in there. There's no point in searching against the human proteome. Okay, we will discuss that more in a bit, but now let's get started with the hands-on part so you can actually analyze some proteomics data.